Okay, matrix algebra and systems. We're going to find matrix inverses, which we did last year. So of this objective, really, there's only a few new things. We did this year, find matrix inverses. We did this last year, determinants. We used inverse matrices to solve systems, but we did not do Cramer's rule. And that's so that this one is new. So again, most of today is a review. So the answer to this is no. But honestly, you really don't divide real numbers either. It's just shorthand by multiplication of the multiplicative inverse. So really dividing by 5 is multiplying by the multiplicative inverse of 5, which is 5 to the negative 1 or 1/5, right? So isn't it true that 5 to the negative 1 is 1/5, 1 over 5, times 5, and that is 1. And we call 1 the multiplicative identity. Okay? So what is true about these two things? These two numbers are inverses of each other. When you multiply inverses, you get the multiplicative identity. Less important to us is the additive identity, right? If you have the number 5 and you want to get the additive identity, it is just the opposite of, right? So 5 and negative 5 are additive inverses because when you add them, you get the additive identity. For matrices, we don't really need the additive identity. It exists, but it's yawn kind of boring. So firstly, hint from the warm-up, what matrix acts like 1, this one? In other words, do we have a matrix that we can multiply by right? That is the multiplicative identity. And that is, think about this, right? What does it mean in real numbers, right? If you have 5 and you multiply it times the multiplicative identity, you don't change it. And that's true for any number, right? Except for 0. 0 times 1 is, 0 times 1 is still 0, sorry. So 5 times 1 is 5, right? So do you have a matrix that I can multiply a matrix by and it doesn't change it? Didn't we see that in the warm-up? Warm up. So yes, we have an identity matrix, but we're going to talk about the identity matrix for a subset of matrices, and that subset is square matrices. There are identity matrices for non-square ones. They're just not uniform. I can't say for every non-square matrix there is one multiplicative identity. But there is if it is square. If you have a square matrix, the identity matrix, capital I sub n, so the identity matrix for a square matrix, 2 by 2 square matrix, has 1s on the main diagonal and 0s everywhere else. The identity matrix for a 3 by 3 matrix has 1s on the main diagonal and 0s everywhere else. Okay, and so on and so forth, and that's what this statement says. Can you think about why you're not allowed to divide by 0? Right? If it is true that any number times its multiplicative inverse is the identity, that works for every number but 0, right? So this is really 5 divided by 5. 0 times the reciprocal of 0. Remember, this is really 5 over 1, so its reciprocal is the multiplicative inverse. Well, this is 0 over 1. What is the reciprocal? That does not equal 1 because this is undefined, right? easy. Right, if you take all right. So inverse matrices. So we have the identity, but we want to know what matrix now. Now think about this for numbers, right? If this is what we just did before was what number times 5 equals the multiplicative identity 1. And it was the multiplicative inverse, or for real numbers, that is the reciprocal. So I want to know in matrix land, what can I multiply by a matrix such that I get the identity? And we're going to start with a 2 by 2 matrix. So what elements would go in here that I would multiply, right? Row by column, row by column, row by column, right? So that I get 1s on the main diagonal and 0s everywhere else. So we're just going to start with a particular instead of in general. We're going to make A, B, C, and D 1, 2, 3, and 4. And I'm going to name the elements of the inverse, right? If I call this matrix A, I want to know what is A inverse such that when I multiply these by the rules of multiplication, I get the identity in the multiplicative identity for a square matrix. So in order to do this, I'm going to actually multiply these. So what happens when I multiply these two matrices? I get x times 1 plus y times 3. So I'm going to multiply these. And I get x plus 3y. Then I'm going to multiply these two, right? 2x and 5y. I'm sorry, and 4y. Next I'm going to go here and multiply z times 1 and 3 times w. And then the last row with the last column, and I'm going to get 2z plus 4w. And that matrix has to equal the identity matrix 1, 0, 0, 1. Well, what does that mean if I take these out of the matrices? Doesn't that mean, right, if I now have corresponding elements, doesn't that mean that x plus 3y has to equal 1? Right? So I just took all this out of here and made, right, 4 equations, and then these two equations here have x and y in them. And I'm going to multiply this by -2. So y must equal 1. But if y equals 1, I'm going to go back to this red equation and say x is equal to 3 times, x plus 3 times 1 is equal to 1. Therefore, x is equal to -2. And I'm going to do the same with my purple system, right? I'm going to multiply this times -2. Add down. Right? I'm going to put that up into here. Z plus 3 times -1/2 equals 0. So z is equal to -3/2. So what did I just do? I found x, y, z, and w. So that means that if you multiply -2, 1, negative 3 halves and negative 1 halves times 1, 2, 3, and 4, you know what you're going to get? Yep. The identity matrix, which means, again, this was A, and I found A's inverse. Well, that was swell, but I'd like to find a pattern so that I don't have to solve a system every freaking time. I forgot that I typed that out. Right? So here's my inverse. I sure would like a way that I could find a pattern for any matrix. What is the inverse of any matrix, any 2 by 2 matrix? Right? So I'm trying to find a pattern for a 2 by 2 matrix. It's not immediately obvious, but it may be obvious if I do this. For no reason than I just feel like it. I'm going to factor negative 1/2 out of our inverse matrix. I'm not going to change it, I'm just going to factor, which means I'm going to divide every element by negative 1/2. What happens when I do that? Divide negative 2 by negative 1/2 and you get positive 4. Right? Right? I'm taking negative 2 and dividing it by negative 1/2. Then I'm going to take 1 and divide it by negative 1/2. That's what it means to factor out negative 1/2, right? And that is negative 2, isn't it? Then I'm going to factor 1/2 out of the 3 halves. So 3 halves divided by negative 1/2. Well, that's negative 3. And then I'm going to take negative 1/2 and divide it by negative 1/2. And that's a 1. So again, you have no idea why I did that. I just did it because I felt like it. It is legal, but now I want you to look at my blue elements right there, and I want you to go back up here and look at my original matrix A. Because remember, my goal is to be able to give you any matrix and you be able to come up with its inverse. Can you see any relationship with these numbers and the numbers in blue? What's true about the elements on the main diagonal? Well, they just got switched, didn't they? Right? 1 and 4 and 4 and 1 just switched. And then what about the minor diagonal? The minor diagonal, the elements stayed in the same position, but they were what? Starting to see a pattern, but I still don't know where this came from. So before we actually go to the pattern, take a moment and I want you to make sure that you believe that the matrix we found that we claim is the inverse, I can either right multiply or left multiply. Remember, we talked about this in the last video, that matrix multiplication is not commutative, except it is when you're dealing with the inverse. So again, take a moment, make sure you believe that this is true, whether I left multiply or right multiply. So the pattern for the inverse of a 2 by 2 matrix looks like this. So take a moment and copy that down. Notice that the inverse of this matrix A has a matrix that we call the adjoint. This is the adjoint of a 2 by 2 matrix. To find the adjoint of a matrix, which is not the inverse yet, that's just a piece of the inverse. The adjoint is switch the elements on the main diagonal and negate the elements on the minor diagonal. That's the adjoint, but that's not the full inverse. The full inverse comes when you multiply each one of the elements of the adjoint by a fraction, and that fraction is 1 over this product, and this product is, you should recognize this, the product of the main diagonal minus the product of the minor diagonal. And of course, since it's in a denominator, this only works if that product is not equal to 0. And you may remember there's a D word for this product. If the product is 0, we can't go on with finding the inverse, and we say you don't have an inverse, and we call that matrix singular. It's all by itself. Poor thing. It doesn't have an inverse. It's so sad. There are formulas for inverses as long as that product is not 0 for any square matrix. They just get more and more complicated. Adjoints get more complicated. It's not just switch the main and negate the minor, and this product down here becomes more complicated as well. So that's what we have calculators for, right? You will have to know how to do 2 by 2 matrices and inverses by hand. So let's practice what we've learned. So find the inverse. So to find the inverse, it's 1 over that product times the adjoint. And remember, the adjoint is switch the elements on the main, negate the elements on the minor. And then this product down here is the product of the main diagonal minus the product of the minor diagonal. So this is 1 over negative 17, which is just a scalar, times the adjoint. I don't care if you multiply that through. I often leave it out. I often leave my inverse this way so that I don't have 4 fractions, right? I just have the 1 out front. How about this one? Right? It's 1 over that product times the adjoint. And the adjoint is switch and negate. And then the product is main minus minor. Uh-oh, what is this? Blows up. This matrix has no inverse. It's singular. So I'm sick of calling that product. Maybe you remember that that product is called the determinant of a square matrix. The determinant of a 2 by 2 matrix is the product of the main minus the product of the minor. Okay? It is a number. The determinant is a number. Notice the determinant, the notation for determinant is det, or what looks like absolute value bars. Again, right, the symbol is in matrix land. It is absolute value. It is not absolute value bars, it's determinant. Here's the formula for the determinant of a 3 by 3 matrix, and this should be familiar from vector land, right? It's just that our first row in vector land was I, j, and k. So it's not, right? So we would have I, negative j, and k in front of the many determinants. Right? Now you don't have, that's not I, j, and k, it's actually numbers. Right? And it's still plus, minus, plus. There are formulas for 4 by 4 and 5 by 4 and 6 by, whatever, 5 by 5 and 6 by 6s. You'll have to do that in your linear. We are doing the, baby linear algebra is what we're doing. But our calculator can do most of these, and it can do all of the calculations that we need. So let's find this determinant. Notice that it's got the determinant notation here, and then we're going to make sure that you know how to check it on your calculator. So it is positive 2 times a mini determinant, negate a negative 1 times another mini determinant, and a positive 1 times another mini determinant, right? And so the first mini determinant is 6 minus 4. The next mini determinant is 0 minus negative 8. Check my math. And the last one is 0 minus negative 6. So that's 2 times 2 plus 1 times 14 plus 1 times 6. So what is that? 24? And let's make sure that you know how to do this on your calculator. Oh, didn't mean to keep that. Second matrix, edit, matrix A, 3 by 3, and it was I've entered it all correctly. Then arrow over to math, and the first choice is determinant. All rats. $18. Is that what I got? No, I got 24. What did I do wrong? First, let me check and make sure all my matrix entries are right. Matrices on the calculator is so clunky. 2, negative 1, 1, 0, 3, 4, negative 2, 1, and 2. So that means that I've done something wrong here. 6 minus 4 is 2. 2 times 2 is 4. Eight. Oh, I added that twice, didn't I? Silly. I did 8 and... Right, 8 and 6 are 14. Is 14. And 14 and 4 is 18. Yay. Right, but you see there making a mistake? I checked both things. I checked data entry and I checked my math to see, right, because I could have made a mistake either way. All right, now moving on to representing systems of equations with matrices. So I kind of sort of did this when I was going through the inverse, right, finding the inverse, multiplicative inverse, right? If I multiply these two matrices, right, so this is a 2 by 2 matrix and this is a 2 by 1 matrix. I can multiply them and my answer is a 2 by 1. So multiply 2x and 3y 1x and 3y. That 2 by 1 matrix is equal to this 2 by 1 matrix. So that is just an algebra system, right? That looks like this. It's just two equations with two unknowns, and I know how to do that algebra, right? I'm just going to subtract these. 2 minus 1 is 1. 3 minus 3 is nothing. 6 minus 9 is negative 3. X is equal to negative 3. So negative 3 plus 3y is equal to 9. 3y is equal to 12, and y is equal to 4. Right, there's my, so these two lines, these are both linear functions. I have an x to the first and a y to the first. These two lines intersect at the point negative 3, 4. Do you remember the vocabulary we said with that? This was an in from AAF. This was an independent, consistent system. Independent, consistent meaning I got an answer that the two lines did meet. Independent meaning that they met at a point. Remember what would happen if we ended up did this and we ended up getting 0 equals 0? Remember what that means? Graphically, that means you have coinciding lines, right? One line lies on top of the other. That is an answer, but it depends on the lines being the same. Do you remember the third case? The lines are parallel, they don't meet. That is not consistent. I don't have an answer. They don't meet. Once or infinitely, they don't meet at all. So that is not consistent. It is inconsistent. Yes, you are responsible for that language, right? I taught it to you last year for a reason. So what if I ask you to solve the matrix equation by left multiplying both sides of the equation by the inverse matrix? What the hee-haw? Okay, inverse matrix. All right, here is matrix A, and they want me to left multiply by the inverse. So remember, you have an equation, so if I multiply this side by the inverse, on the left, I must left multiply this side of the equation as well. So let's do that. Notice that when you multiply A inverse times A, which I haven't even done yet, what happens here? What do you get? Don't you get the identity matrix? And what's the identity matrix times xy? Yes, it is just xy. So I wrote over here, here is me left multiplying, because if you left multiply on this side, you got to left multiply on this side as well. So here's me saying I am left multiplying by A inverse, multiplying 6, 9, and I got negative 3, 4. Now I didn't actually do this, right? I just did this on my calculator. So in my calculator, I put 2, 3, 1, and 3, and then I also put in the answer matrix. Again, we did this last year, so you can look back at it in your notes. And put in the answer here. And I'm not actually going to find the inverse. Now, last year I always made you write out, right? You had to write out the inverse that you found because I was testing the objective of finding the inverse. Here, that's prerequisite knowledge, right? So I just need you to understand what you're doing, which is why we reviewed this. And then you can just use your calculator and say, what I want to do is I want to take matrix A, its inverse, right? A inverse, and multiply it times the answer matrix, which I put in matrix B. Bam! -3, 4. Oh, snap. So this will hold for any square system. For any square system of equations, if you left multiply by the inverse to eliminate the coefficients and left multiply the answer matrix by that same inverse, you will get the variable matrix X by itself. This is called the inverse matrix method for solving a matrix equation which represented a system of equations. Now, I wouldn't really do this for a 2x2, but I would for a 3x3 or a 4x4. So the inverse matrix method is one method of using matrices to solve a matrix equation. A matrix equation where you have a matrix times a variable. These are your variables. These are your coefficients times your variable matrix is equal to B, C, or whatever you call this. When we were in, I don't know if you remember or not, but when we were in AAF, I'll call it the SVA. Coefficient matrix times the variable matrix equals to the answer matrix. And I made you multiply by the inverse of the coefficient matrix on both sides, right? Because this was the identity, and you got the variable matrix is equal to the inverse of the coefficient matrix times the answer matrix. So I used to use that notation last year. This is more typical what you see in a math book. And of course I used B in my calculator for this matrix. This C stands for constants, right? These are constants. That's why they call that matrix C. But do you see, right, the relationship to Algebra 1, right? An Algebra 1 equation where you have, for instance, 2x is equal to 6. You multiply by the multiplicative inverse of 2 on both sides. So you get the identity, multiplicative identity 1, and then you actually multiply 1/2 times 6, which is 3, and then generally you drop the identity and write the right in front of the x. That's exactly what we did here. To solve the matrix AX is equal to C, you left multiply by the inverse, and then you don't generally write the identity matrix, right? Because the identity matrix times the variable is just the variable matrix. So here was another one for you to try, right? Just put this into your calculator. What do we have this time? Just go and edit. Second matrix, edit matrix A, and make it 2, 8. Whoops. Edit matrix B to be the constants. And multiply. Whoa! What? Hey! What's the matter? Oh. Singular matrix. What does that mean again? Where did we come across singular? Oh. That must mean, remember, what we were trying to do here Remember what we were trying to do here is say, right, multiply by the inverse. But the inverse is, right, the inverse is 1 over the determinant, and look at the determinant of this. Negative 24 minus negative 24, which is 0. So there's no inverse, which means, now here's the issue. I don't know whether this, I know this is not independent. But inverse matrices doesn't tell me. So maybe this is dependent, consistent, or maybe it's inconsistent. Now I can do algebra and figure this out, but inverse matrices doesn't tell me. So that means that's a limiting issue for inverse matrices, right? If I have a system, if I have a solution, it gives it to me. But if I don't have an independent solution, it's not an independent consistent system, inverse matrices can't differentiate between these two. There must be some other way then. Before we do that though, let's do a word problem. Okay, so I want you to use matrix algebra and systems to solve this word problem. And one of your homework problems is like this. So I have tickets for a haunted house, and I have one kind of ticket, another kind of ticket, and another kind of ticket. So I have $4.50 times one kind of ticket, and $7 times another kind of ticket, and $12.50 times another kind of ticket. And that's all money. Can you find some total here in the words that's money? Give me the money. Well, that's one equation with 3 unknowns. So I need 2 more equations. So what other total do I have here? That total has nothing to do with money, does it? It just has to do with preschool scary plus ghost and goblin scary plus blood and guts scary. Well, now I have 2 equations with 3 unknowns. I can't solve that until I have 3 equations with 3 unknowns. So what's left? I've used this, and I've used this. Oh, what's this say? The sum of the $7 tickets and the $12.50 tickets. The sum of those tickets, not the money of the tickets, but the sum of Y plus Z tickets must be there's my equal sign, 702 less than the number of the X tickets. Okay, there's my system. Can you take that from algebra into matrix world? What's my X? Right, it's not 1. Right, you need to move that over. The coefficient is -1. So that's matrix A. My variable matrix is X, Y, and Z. And my constants.
Yeah. All right.
How was it?
Chamava. Are you recording video?
Yeah.
Yeah.
Mother to you too. So this, again, how I solve this is left multiply by the inverse. And you just do that in your calculator. Okay? And let's see, I don't know if I wrote down what that was. Oh, I did. I got, when I was done, I got the number of preschool scary tickets was 12. I think that's 452. You have to check my right. I can't tell if my 4 is a 9 or a 4. The number of Ghost and Goblin scary tickets was 9,270. And the number of Blood and Guts scary is, oh gosh, my writing is terrible. I think it's 2480. But you guys check that out for me, okay? So again, when you were in AAF, I made you write out a lot more of what the inverse is. You know, I had you write out the elements of the inverse and all that kind of stuff. I don't need to see that now. I just need to see your algebra setup. Show me how you wrote the matrix. Then use your calculator. Tell me that you did use the inverse, right? Write me the matrix equation. And then just give me the answer. Oh, Kramer. What a wig. What a wig. That Gabe. What a guy. I want to solve this 2x2 system. By the way, I can solve this with algebra and I solved it with inverse matrices. Right? I already know the answer. But we're going to solve this by Kramer's rule. Now, Kramer did a lot of stuff in vector land and linear algebra land. His rule also is called the determinant method. Because it uses determinants. So I'm going to do this for a 2x2 matrix, but the exact same process holds for 3x3s, 4x4s, and all this kind of stuff. So Kramer's rule uses 3 determinants. The original determinant of your original matrix A, but we do not find inverses. Then you're going to find you're going to find 2 more determinants, and those determinants are found by replacing each column at a time. So this is called the determinant of matrix A with the X column replaced. So notice the X column was taken out and it was replaced. What was it replaced by? The constants. Find that determinant. Then you find another determinant where it's called the determinant of A sub y, where the y column is replaced, and it is replaced with the constants. So let's calculate these determinants, right? What do I have? 6 minus 3. This is 18 minus 27. And this is 18 minus 6. And then Kramer said that the solution, once you have these 3 determinants, the solution xy looks like this. The x component is the determinant A sub x over the original determinant, and the y answer is the determinant of y over the original, right? The determinant of A sub y over the original determinant. Now this all, again, this all has to do with something we're going to be touching on the next video, and then really in linear algebra as to why this works. It was a proof that he did based on some work that Gauss also had done. Or I don't know, I have to look that up. I don't remember who came first, Gauss or Kramer. But anyway, look at what this reduces to, right? What is this? Negative 9 over 3 is negative 3. 4. Isn't that the answer we came up with before? OMG. So this is the determinant method, or Kramer's rule, for solving the matrix equation AX is equal to constants. And that works for a 3x3, right? If this had been a 3x3 system, you would just have to find another determinant. It would be determinant of A sub what? right? And then you would find x, y, z, and the z component would be whatever that determinant was over 3. Right? Now the nice thing is that Cramer's rule can tell me, so this system was independent consistent, right? So if Cramer's rule can tell me about the other, if the determinant of the original matrix is 0, and so are all the rest, your a sub x, your a sub y, and if it's a 3 by 3, a sub if everybody's a 0, then you are dependent consistent. However, if the determinant of A, your original determinant is 0, but the other ones are not equal to 0, and it only takes one. Only takes one. I don't care which one. I don't care if it's all of them or whatever, but if one of the determinants is not equal to 0, then you are inconsistent. Right? So if I had done, so for instance, if we had done this and I had had instead of 2, 3, I had this, right? 6 minus 3, 6 minus 6 is equal to 0. And then this matrix had also, let's pretend this matrix had turned out to be 0 and this matrix had turned out to be 0. I would end up with a bunch of 0 over 0s, right? My system would look like 0 over 0. That means that's dependent, where everybody's 0. But if instead I had had the original determinant equal to 0, but this determinant, let's say, had been equal to -9, I would have ended up with 0 over, -9. -9 on top of 0. Can't divide by 0. That's undefined. That's inconsistent. So Cramer's rule doesn't use inverse matrices. It's a little bit clunkier. I can do this on my calculator, but I have to create a whole bunch of I have to calculate I have to create a whole bunch of matrices and then find their determinants. But Cramer can tell me, can go all the way with determining and differentiating between inconsistent, independent consistent, and dependent consistent. So why don't you practice with 3 by 3s? All right, so I want you to take this same system and I want you to solve it using inverse matrices, and I want you to also solve it using Cramer's rule. Okay, so you can pause and do it yourself, or watch me. I'm not going to use the calculator, but I will go through the setup. I'm going to take the inverse of that matrix and multiply it times 24, 0, and 12. And that is going to equal my x, y, and z. Okay, so you just need to go into your calculator, create this 3 by 3 matrix, put that in A, put the constants in matrix B, and then type on your calculator A, right? The variable that you're looking for, the variables that you're looking for are A inverse times B. For Cramer's rule, your matrix equation, right? You know what the matrix equation looks like. but I need 4 determinants. So the first determinant I need is the determinant of 4 right? And I'm just going to use my calculator. I mean, you can do this by hand. You know how to do a 3 by 3 determinant by hand, but you don't have to. You can use, right, your calculator to get that. So that's your first determinant. Then you're going to do the determinant a sub x. Whoops. A sub y. A sub z. And replace the respective columns with the constants. And then you're going to get numbers for these, right? And then your solution is whatever ax was over the original, whatever ay was over the original, and whatever az was over the original. Okay? All right. I hope you have a good rest of your day. Take care.